Inertial confinement fusion is a very different solution to the magnetic confinement reactors discussed previously. It was inspired by the hydrogen bombs developed in the 1960s, in which a fission reaction compresses fuel to create a massive, uncontrolled fusion reaction that releases much more energy than the initial explosion. The aim was then to find the threshold at which sufficient energy is produced without causing an uncontrolled reaction, by reducing the amount of fuel used per ignition. For inertial confinement fusion, a tiny pellet of fusion fuel is irradiated with powerful lasers or high-energy particles. This creates an explosion on the outer layer as it heats up. This explosion compresses the inner layer, sending shock waves to the center, further compressing and heating it. This process is successful when the energy of alpha particles created in the explosion matches the energy lost by X-rays, and the center ignites to create self-sustaining fusion, and a large amount of energy is produced. There are two methods for the initial heating, direct and indirect. The direct method involves shooting the lasers directly at the fuel capsule. This is the most efficient method, but requires incredible precision, as any spherical asymmetry will cause the fusion to fail, as the explosion is off-center. In indirect heating, however, the capsule is put inside a metal tube called a hologram. This is irradiated with the lasers to heat it to X-ray temperature, at which point it irradiates the fuel capsule symmetrically, and the fusion process can occur. This method allows for wider, less precise lasers, but wastes a lot of energy in heating the hologram. Inertial confinement is currently far from being economically viable, but on August 8, 2021, the National Ignition Facility in the US produced a 70% energy yield, with more than 1.3 megajoules of energy produced, which is the current world record.